So let's start with the following. Given two immersions of complementary dimensions, y and y and n1 plus n2, so well, and I1 and trivial. So assume all the double points are transverse. I probably didn't define this for two different immersions, but it's clear what I mean. Yeah. So transverse double points. Okay, now I can do the following. Well, okay, let me simplify it a bit first. So in the simply connected case, it was probably already defined in the previous talk. So I can look at the double point and assign an index to this, depending, well, +1 or -1, depending on whether the f1 x, so x1 is an n1, x2 is an n2. Depending on whether this preserves the orientation, or -1 otherwise. Yeah. Clear. Now I can define the geometric intersection number of two I1 m trivial immersions, transverse immersions. By summing all these local indices over all the double points. Yeah, and this is an integer. So in the non-simply connected case, remember n. Well, I want to take into account the action of pi1. So what I do, I lift my immersions. So the lifts go from n and I, and are still immersions to the universal cover of m. But a double point here is not necessarily a double point of these two immersions. But there is an element g of x in the fundamental group of M, which with this property. Yeah. So I mean, I know once I project everything to M, this is a double point, so it must sit in the fiber, so it must differ by so the image of x2 under f2 must differ by a translate from the image of x1 under f1. Well, now I can do the same, so I can assign to x an index plus or minus depending on if f1 f1 x1 plus d dgx f2x2 preserves the orientation, orientation, or 0 minus either plus g of x or minus g of x. Does it make sense? Okay, so the same, I lift it to the universal covers. It's not necessarily a double point, so they might differ by g. I just compute my usual index and add a g. So I put the intersection index of a double point of 2 pi 1 and trivial transverse emergence to be plus or minus g, depending on the orientation behavior. And the geometric intersection of 2 pi 1 and trivial transverse emergence is now the sum of all double points of the local indices. And this lives here, this is not. Okay, so this is clear, yeah. Small remark which will matter later is if I change the order, I get the sign here. So it is minus 1 to the n1 and 2. Index of x2, x1, and the evolution of this. Just as a reminder, the evolution sets an element g to the element omega g and g index. Omega g was this orientation character. So if you want to simplify this, imagine x is or m is an orientable manifold, and this disappears. Okay. Okay, so the main proposition, which I'm not going to prove, is for 2 transverse I1 and trivial emergence the geometric and the algebraic intersections coincide. Why is it important? So, any ideas? Well, I mean, first of all, this is a homological invariant and this is a geometrical invariant, so it means I can start with emergence which are not necessarily transverse, make them transverse. This is always possible up to homotopy. This doesn't change the algebraic number, but it makes a definition of the geometric one possible. So this is, you could view this as an extension of this. Well, I mean, it will matter at the end of the talk as well. Somehow, I mean, why am I not going to prove this? There is just not enough time. So in most books, you won't even find this because this is somehow more or less known. The proof, a concise proof in Andrew's book uses, well, say, Thom isomorphism, transfer maps, and somehow an interpretation of the geometric index homological interpretation already. I mean, this is the main ingredient. So you find in other books, you find that the intersection number, the geometric intersection number, is a homological invariant. And how do you show this? I mean, you can pass, you have two immersions. You can take a tubular neighborhood around one of the images, and then you look at the intersections of this tubular neighborhood with the other manifold. Yeah? So say you choose a tubular neighborhood of N1, and you look at the intersections of N2 and N1, and you will have several like disks or something. And this is already somehow homological, because then you only count orientation and behavior. But you have to pass from N1 to the, say homologically, to pass from N1 to the tubular neighborhood of N1, and this is the Thom isomorphism. So you just take the Thom isomorphism of the tubular, of the normal bundle in the bigger manifold. So another proof, the source I found is Davis and Kirk lectures on algebraic topology, or in algebraic topology, which is theorem 10.3.2. I mean, this is not the only source. It's just in other books it's not stated explicitly like this, because it is clear for other reasons. Or Andrew's book. Okay. Okay, let me now go on and talk about the Whitney trick, and if there is time, I try to talk about an example along these lines. I mean, there are several examples you can think of now. If you embed N1 and N2 into N1 cross N2, for example, so what's their algebraic intersection? Because now you see it geometrically just one. So somehow it is enlightening in both ways. Yeah. Okay, the Whitney trick. Okay, I mean, this is you might anticipate already that this is an important result, and of course it is. I'm not going to prove it, but I will give you an idea of how this is actually proved. So given two by 1m trivial embeddings,